Hello, I'm Hongrui Huang. For robots to operate in our households, they need to be able to perceive common objects. One common class of object is liquid, such as sauces, drinks, detergents, and so on. In this video, by shaking the containers, humans can use tactile sensing to quickly answer questions like how much liquid is left, how viscous the liquid is. We want to enable robots for such an ability. When we interact with the bottle, different liquids will have different movements, which is caused by the liquid properties. In this work, by interacting with the container, we want the robot to infer liquid volume and viscosity in the container by only tactile sensing. A common approach is to learn to predict liquid properties using the tactile patterns in a purely data-driven way. However, these data-driven approaches often require a lot of data and suffer from low accuracy. Another approach is to build the physics-based model by analyzing the fluid dynamics of the liquid content. However, their model is limited to cylinder containers with precisely known dimensions. Our approach complements the data-driven and physics-based approaches by modeling the principal liquid dynamics with simple physics and learning the complex on-model dynamics in a data-driven way. We call it a physics-inspired approach. When a resting container is perturbed, the surface of its liquid content will oscillate and gradually decay away. When analyzing the system energy using the principle of working energy, we can see that the system oscillates because of the energy exchange between the kinetic and potential energy. The oscillation decays because the liquid's viscous force acts like friction and dissipates the system's total energy. We therefore derive that the system is a second-order system. Most importantly, the decay rate is governed by the liquid viscosity, and the oscillation frequency is governed by the liquid surface height. In our method, the gripper first grabs the bottle with two GelSight tactile sensors and make an impulse movement. We collect the dynamic tactile signals during the free oscillation period. We track the markers of GelSight, extract the tactile data, and fit it with a damped oscillation signal. As the physics-inspired model suggested, the decay rate lambda and the oscillation frequency omega of the damping signals are highly relevant to the liquid viscosity and height. We learned this relation in a data-driven way because it is affected by the complex shape of the container and the on-model dynamics. We take multiple experiments to prove our method. First, we try to classify three common liquids: water, oil, and detergent. Their viscosities are different, leading to different oscillation decay rate lambda, which can be perfectly extracted by our method. We achieve 100% classification accuracy for water, oil, and detergent, even without fixing their weight and amount. In addition, the model can be trained with only 24 data points, showing our method is data efficient. Secondly, we target on liquids with smaller differences, the sugar water with different concentration and height. We train a Gaussian Process Regression model using lambda and omega as input and regress on the sugar concentration. We achieve a concentration regression MAE of 15.3% and log viscosity prediction MAE of 0.16. It shows that our method can estimate the concentration of sugar solution by only tactile sensing. We use the same dataset and method to regress on the liquid height. We achieve a height regression MAE of 0.56 mm, which is near the limit of the ruler's precision. Additionally, the same model can also be used to estimate properties of unseen liquids, such as marine. We also show our methods can be generalized to different containers, such as large cuboid container and a cylinder container. In addition, the model can be transformed between different containers. Based on the trained model of the groove cuboid container and limited amount of fine-tuned data on a new cuboid container in different size, we can fit a model for the new container. With only 15 fine-tuned data, the tuned model can predict well, with a concentration prediction MAE of 19.3%. To conclude our work, we propose a physics-inspired model of the liquid container system for dynamic tactile sensing. Based on this, we achieve liquid viscosity and liquid height estimation. We also show our method can be generalized to different liquids and containers. Thank you for watching.